Okay, so page 348, and we are still in chapter 6, section 3. This is example, whichever the last one was, so I think that was 13, so this is 14. That's what was on this page. Okay, so we're talking about drive times. This is the average drive to work is 9.6 miles. So right there, that's our mu, which is also the same as mu subscript chi bar. Assume the standard deviation is 1.8 miles. So there it just says the standard deviation. And so that is from the original distribution. Remember, that is the one that we're going to have to divide by the square root of the sample size. If a random sample of 36 employed people, okay, so there we are, n is equal to 36. The square root of that is not going to be too bad, so that'll be okay. All right. Random sample of 36 employed people who drive to work are selected. Find the probability that the mean of this sample number of miles driven to work is between 9 and 10 miles. Okay, so here we're looking for, let's denote this as the probability that our chi bar, remember, because we're talking about the average number of miles of a sample of 36 people, is between 9 and 10 miles. Okay, so that's what we're going to look at. Oh, hang on, focus. There we go. I thought it was just my glasses for a second there. All right, so let's begin by sketching the distribution. This is, well, basically, oh, well, it looks a little bit poor, but oh well, just a sketch. Remember, approximately normal is okay. All right, so our average is 9.6. I guess I'll just go ahead and sketch the data values instead of their z-scores. Here is 10 right here, and here is 9 over here. Okay, so it looks like this z-score is going to be positive something, this z-score is going to be negative something, and we're looking for this area in here. Okay, so the first thing that we're going to do is we're going to calculate our z-scores corresponding to these x values. Or sorry, not x values, chi bar values. Should kind of make that distinction. So let's start with the left one. We'll do 9 minus 9.6, all divided by not just 1.8, but 1.8 divided by the square root of 36. So we'll do that. And let me pause to just go ahead and plug that into my calculator. Okay, so my calculator told me that this is equal to -2. And then similarly, we're going to compute the z-score for chi bar equals 10. So we'll be plugging in this. Oh my gosh, look at that. I forgot to write down the formula first things first. Oh, silly me. Will I ever learn? No, I probably will not. Okay. We'll never practice what I preach. All right, let's pause and let me calculate this. You can go ahead and plug these numbers in, but hopefully you can see where I'm getting this. So I'm substituting 10 for chi bar, 9.6 in place of mu, 1.8 for sigma, and then we have to include the square root of n. So this whole denominator is going to be 1.8 divided by the square root of 36. So when I'm doing this let me just pause and do it. Yeah. So what I was thinking about saying was, notice that when I'm plugging this in into the calculator, I'm putting in a lot of parentheses. I'm going 10 minus 9.6, all in parentheses before I do the first division, and then divided by. Notice this whole thing is what I'm dividing by. I'm dividing by 1.8 itself divided by the square root of 36. So inside here, there's lots of parentheses. I have parentheses for the whole downstairs portion of this, the whole denominator. And then inside that, I have 1.8 divided by, and the square root comes with parentheses. So I have to make sure to not forget to close any of those off. Most of the time, if you just hit enter, it'll work out okay. So there are our z values. Now what do we do? Well, we have to find the area corresponding with our picture here. All right, so let's do that. All right, well, I was considering pausing and showing you a little screenshot of each of the z values that I looked up, but instead I just magically wrote them down. So here I have the probability that z is less than -2, and that is 0.0228. Okay, so basically that's just looking up right here, plugging in -2, and can't really see that. Yeah, there, that is that one right there. Okay, so that one was easy. Then similarly, I went ahead and looked up the probability that z is less than 1.33. So that just means, remember, since these are left areas, everything's going to be a probability that the z is less than. Okay, so that one we just look up 1.33 on the other side of the page. We get out 0.9082. And then the probability that the z value is going to be between these is just this one minus this one. So that's why I subtracted here. Okay, so up here you can see this left area is 0.0228. This left area, everything to the left of this z-score corresponding to chi-bar equals 10 is 0.0982. And then inside here, this would be our probability attached to that. Woo. Okay, so that finishes up that one, because that is our final answer. That would be, yeah, what we're looking at there. That's the probability that our selected 36 employed people, that's our sample, and that's our sample size. Remember, n was 36, that their drive to work, their average as a group, is between 9 and 10 miles. All right, so let's pause for a moment and move on to the next example. That would be example 6-15 on the next page over. Okay, so I unpaused before I unpaused. So at anyway, in part A, we are dealing with essentially a sample size of 1. So here, if we take our standard deviation and we divide it by the square root of 1, that's not going to change it. Basically, our z-score is going to be the value from the distribution. And if we're looking at it as a sample of size 1, well, the average of one thing would just be that single thing itself. The average is still the average, right? And then the standard deviation is just the standard deviation by itself. In part B, we're dealing with a different sort of scenario. We're going to be seeing a sample of 40 randomly selected. And so our z-score is going to be from a different distribution. We're thinking about taking those 40 construction workers and averaging their number of hours per worked on the weekend. The mean value for this distribution is the same as that. So that's going to stay the same. But then the standard deviation for the distribution of sampling means is going to be here, putting in 40 in place of n. So that's going to be the difference between these two questions. They seem like the same type of question. They're both asking, what's the probability that, the number of hours worked over the weekend is going to be greater than 8. There's Was that the question, or was it a less than? Oh, sorry, not greater than, says fewer than. But in the one case, we have a sample size of 1. In the other case, we have a sample size of 40. So the question to kind of consider here before we pause and move on to answer it is which do we think would be more? Would it be more likely for one single person to work fewer than 8 hours over this weekend, right? Or if we take a whole group of 40 people, would they have a higher likelihood of working for fewer than 8 hours? So, that's just over the average. All right, so you would expect the probability for both of these is going to be right around 50%. But we'll kind of pause there and come back and see the difference in terms of doing the problem. Okay, so what happened here? I sketched the distribution. Here's 8. And we went ahead and calculated the z-score as 8 minus 7.93, just divided by 0.8, because here we're just using sigma. And we get 0.09, right? So that's to be expected. We're real close to the average value, so our z-score is going to be real close to 0, right? So then the probability or the area associated with this, the area underneath the curve, is 0.5359. Just looking up that z-score in there. All right, so what's the difference between this and when we have a sample size of 40? Well, remember, we're going to have to plug in that 40 in here in the square root. So we'll come back and do that and compare notes. Okay, so here what happened is when we plugged in 40 in place of n, 0.8 is the sigma, the standard deviation for the original distribution. And we took it and we divided it by the square root of 40. And so that gave us approximately 1.26. Notice that that is much smaller than the original standard deviation, the original sigma for the original distribution. It's about 6 times small. All right. And so notice what happened to our z-score. The original z-score here is 0.9. We're dividing by something that's a lot smaller, 6 times as small. So notice here the z-score 0.55 is almost exactly, what's that? 9 times, look, hang on one second. 9 times 6 times as big. That's about 54.55, pretty close, I'm just saying. Okay, that's the difference between looking at a sample size of 1 versus a sample size of 40. Okay, so if I just randomly grab one single person and say, hey, like, did you work less than 8 hours? Well, the average is 7.93. Yeah, okay, about a 50-50 shot, right? Versus if I go and grab a whole set of people, 40 to be precise, and I say, oh, okay, how long did you work? And you say, okay, well, yeah, I worked less than 8 hours, right? And remember, 8 is right around the average. There's a greater proportion who are, because even though it's right around the average, it was still above the average. And you can kind of see these aren't supposed to be super accurate. But since our standard deviation here is a lot lower, that means that this bell-shaped curve and this bell-shaped curve are different in the sense that this one's taller and steeper and sort of narrower in the middle, whereas this one is maybe like a little shorter and kind of widened out. And so even though we're in the same relative position, the standard deviation really affects the area underneath the curve, because here it's all squished together, and so there's a greater proportion of the area. We have a higher likelihood that this group of larger amount of people has this average, as opposed to taking one single person. All right, so let's conclude.